the validity of special relativity is a consequence of the fact that in some sense it doesn't matter in what order you do these underlying things, so long as they respect this kind of set of causal relationships. So,
and that's the part that's in a certain sense is a really important one, but the fact that it sometimes doesn't matter, that's I don't know. That's another like beautiful thing.
So there's this idea of what I call causal invariance.
Causal invariance, exactly.
Right. So that's
really powerful
it's
idea.
A powerful idea which has actually arisen in different forms many times in the history of mathematics, mathematical logic, even computer science. Has many different names. I mean, our particular version of it is a little bit tighter than other versions, but it's basically the same idea. Here's how to think about that idea. So imagine that, well, let's talk about it in terms of math for a second. Let's say you're doing algebra and you're told, multiply out this series of polynomials that are multiplied together, okay? You say, well, which order should I do that in? Say, well, do I multiply the third one by the fourth one and then do it by the first one, or do I do the fifth one by the sixth one and then do that? Well, it turns out it doesn't matter. You can multiply them out in any order, you'll always get the same answer. That's a property. If you think about kind of making a kind of network that represents in what order you do things, you'll get different orders for different ways of multiplying things out, but you'll always get the same answer. Same thing if let's say you're sorting, you've got a bunch of A's and B's. They're in some random order, BAA, BBB, AA, whatever. And you have a little rule that says every time you see BA, flip it around to AB, okay? Eventually, you apply that rule enough times, you'll have sorted the string so that it's all the A's first and then all the B's. Again, there are many different orders in which you can do that many different sort of places where you can apply that update. In the end, you'll always get the string sorted the same way.
I know with sorting a string, it sounds obvious. That's, to me, surprising. That there is, in complicated systems, obviously with a string, but in a hypergraph, that the application of the rule, asynchronous rule, can lead to the same results sometimes.
Yes, that is, it is not obvious, and it was something that I sort of discovered that idea for these kinds of systems back in the 1990s, and for various reasons, I was not satisfied by how sort of fragile finding that particular property was. And let me just make another point, which is that it turns out that even if the underlying rule does not have this property of causal invariance, it can turn out that every observation made by observers of the rule can impose what amounts to causal invariance on the rule. We can explain that. It's a little bit more complicated. I mean, technically, that has to do with this idea of completions, which is something that comes up in term rewriting systems, automated theorem proving systems, and so on. But let's ignore that for a second. We can come to that later. But
is it useful to talk about observation?
Not yet.
At this point?
Not yet.
Okay. Great. So there's some concept of causal invariance as you apply these rules in an asynchronous way. You can think of those transformations as events. So there's this hypergraph that represents space and all of these events happening in the space, and the graph grows in interesting, complicated ways. And eventually the froth arises of what we experience as human existence. So
that's some version of the picture, but let's explain a little bit more.
Exactly. What's a little more detail like?
Right. Well, so one thing that is sort of surprising in this theory is one of the sort of achievements of 20th century physics was kind of bringing space and time together. That was, special relativity, people talk about space-time, this sort of unified thing where space and time kind of are mixed. And there's a nice mathematical formalism in which, space and time sort of appear as part of the space-time continuum, the space-time, 4 vectors and things like this. We talk about time as the 4th dimension and all these kinds of things. It's, and it seems like the theory of relativity sort of says space and time are fundamentally the same kind of thing. So one of the things that took a while to understand in this approach of mine is that in my kind of approach, space and time are really not fundamentally the same kind of thing. Space is the extension of this hypergraph. Time is the kind of progress of this inexorable computation of these rules getting applied to the hypergraph. So they seem like very different kinds of things. And so that at first seems like, how can that possibly be right? How can that possibly be Lorentz invariant? That's the term for things being, following the rules of special relativity. Well, it turns out that when you have causal invariance, and let's see, it's worth explaining a little bit how this works. It's a little bit elaborate, but the basic point is that even though space and time sort of come from very different places, it turns out that the rules of sort of space-time that special relativity talks about come out of this model when you're looking at large enough systems. Mm-hmm. So a way to think about this, in terms of when you're looking at large enough systems, the part of that story is when you look at some fluid like water, for example, there are equations that govern the flow of water. Those equations are things that apply on a large scale. If you look at the individual molecules, they don't know anything about those equations. It's just the sort of the large scale effect of those molecules turns out to follow those equations. And it's the same kind of thing happening in our models.
I know this might be a small point, but it might be a very big one. We've been talking about space and time at the lowest level of the model, which is space, the hypergraph. Time is the evolution of this hypergraph. Mm-hmm. But there's also space-time that we think about in general relativity for special relativity. Like how do you go from the lowest source code of space and time as we're talking about to the more traditional terminology of space and time?
Yeah, right. So the key thing is this thing we call the causal graph. So the causal graph is the graph of causal relationships between events. So every one of these little updating events, every one of these little transformations of the hypergraph happens somewhere in the hypergraph, happens at some stage in the computation. That's an event. That event has a causal relationship to other events in the sense that if another event needs as its input the output from the first event, there will be a causal relationship of the future event will depend on the past event. Mm-hmm. So you can say it has a causal connection. And so you can make this graph of causal relationships between events. That graph of causal relationships, causal invariance, implies that graph is unique. It doesn't matter, even though you think, I'm let's say we were sorting a string, for example. I did that particular transposition of characters at this time, and then I did that one, then I did this one. Turns out if you look at the network of connections between those updating events, that network is the same. If you were to
I see. Yeah.
The structure. So in other words, if you were to draw that if you were to put that network on a picture of where you're doing all the updating, the places where you put the nodes of the network will be different, but the way the nodes are connected will always be the same.
So, but the causal graph is it's kind of an observation. It's not enforced. It's just emergent from a set of events.
It's a feature of okay. So what it is,
a characteristic, I guess, of the way events happen.
Right. It's an event can't happen until its input is ready.
Right.
And so that creates this network of causal relationships, and that's the causal graph. And the next thing to realize is, okay, when you're going to observe what happens in the universe, you have to sort of make sense of this causal graph. So, and you are an observer who yourself is part of this causal graph. And so that means, so let me give you an example of how that works. So imagine we have a really weird theory of physics of the world where it says this updating process, there's only going to be one update at every moment in time. And there's just going to be like a Turing machine. It has a little head that runs around and is always just updating one thing at a time. So you say, I have a theory of physics, and the theory of physics says there's just this one little place where things get updated. You say that's completely crazy because, it's plainly obvious that things are being updated sort of, at the same time.
Asynchronously, yeah, or
right.
at the same time, yeah.
But the fact is that the thing is that if I'm, talking to you and you seem to be being updated as I'm being updated, but if there's just this one little head that's running around updating things, I will not know whether you've been updated or not until I'm updated. So in other words, when you draw this causal graph of the causal relationship between the updatings in you and the updatings in me, it'll still be the same causal graph. whether even though the underlying sort of story of what happens is, oh, there's just this one little thing and it goes and updates in different places in the universe. So
is that clear, or is that a hypothesis? Is that clear that there's a unique causal graph?
If there's causal invariance, there's a unique causal graph.
So it's okay to think of what we're talking about as a hypergraph and the operations on it as a kind of Turing machine with a single head, like a single guy running around updating stuff. Is that safe to intuitively think of it this way?
Let me think about that for a second. Yes, I think so. I think there's nothing. It doesn't matter. I mean, you can say, okay, there is one. The reason I'm pausing for a second is that I'm wondering. Well, when you say running around, depends how far it jumps every time it runs around.
Yeah, that's right. But I mean, like one operation at
yeah, you can think of it as one operation.
It's easier for the human brain to think of it that way as opposed to
well, maybe it's not okay. But the thing is, that's not how we experience the world. What we experience is we look around. Everything seems to be happening at successive moments in time everywhere in space.
Yes.
That is and that's partly a feature of our particular construction. I mean, that is, the speed of light is really fast compared to, we look around, I can see maybe 100 feet away right now. It's my brain does not process very much in the time it takes light to go 100 feet.
The brain operates at a scale of hundreds of milliseconds or something like that. I don't know.
Right.
And the speed of light is much faster.
Right. Light goes in a billionth of a second, light has gone a foot. So it goes a billion feet every second.
There's certain moments through this conversation where I imagine the absurdity of the fact that there's two descendants of apes modeled by a hypergraph that are communicating with each other and experiencing this whole thing as a real-time simultaneous update with I'm taking in photons from you right now, but there's something much deeper going on
right
here.
It does have
it's paralyzing sometimes to just to remember that.
Right. No, I mean, but so,
Sorry.
yes. No,
as a small little tangent, I just remembered that we're talking about, about the fabric of reality.
Right. So we've got this causal graph that represents the sort of causal relationships between all these events in the universe.
Yeah.
That causal graph kind of is a representation of space-time, but our experience of it requires that we pick reference frames. This is kind of a key idea. Einstein had this idea that what that means is we have to say, what are we going to pick as being the sort of what we define as simultaneous moments in time? So, for example, we can say, we set, how do we set our clocks? If we've got a spacecraft landing on Mars, do we say that it, what time is it landing at? Was it, even though there's a 20-minute speed of light delay or something, what time do we say it landed at? How do we set up sort of time coordinates for the world? And that turns out to be that there's kind of this arbitrariness to how we set these reference frames that define sort of what counts as simultaneous. And what is the essence of special relativity is to think about reference frames going at different speeds and to think about sort of how they assign what counts as space, what counts as time, and so on. That's all a bit technical, but the basic bottom line is that this causal invariance property, that means that it's always the same causal graph, independent of how you slice it with these reference frames. You'll always sort of see the same physical processes go on, and that's basically why special relativity works.